Alright, welcome to 1.07. So as we move on from limits, and we're never really going to move on from limits, we're just going to start applying them in more meaningful ways as we go along. So limits are going to kind of be, if you will, like the letters in the alphabet, right? We're going to utilize them in many different, but all kind of inherently similar ways to discover and define some new concepts. And the concept that we're going to start discussing now is continuity. So today we're going to identify points of discontinuity in algebraic or graphical form by applying the definition of continuity, or in other words, what does it mean to be continuous? So we're going to take a look at an example, and then we're going to define a continuous function and take a look at some examples of where functions are not, in fact, continuous. Okay, so let's take a look at a motivating example. Let's say you're a scientist and you go out and you measure the temperature at certain days throughout the year, and you plot these data points. Well, this is great and all, but what might make your findings more useful and more applicable? What you might be thinking is, yeah, these points are great, but what I really want to know is points that are not there. And so I've got to figure out the pattern. Now, pattern is just a kind of a simplistic word for function, right? I would like some function that is going to be a smooth curve like this. And why is that? Well, notice that this curve, instead of just having points all over the place, what this has is that the outputs that you're getting are always, they're continuous, right? There's never going to be some missing output. So for any input, as you move along, you're going to have outputs that are continuously moving along this pattern. And so this is what's called a continuous function. And as we discussed earlier in the unit, right, we said a continuous function is a function that you can draw without lifting your pencil off of the paper. And that's going to be a very reliable intuition to have in the back of your mind as we move on with continuous functions. However, we do want to define this rigorously. So what we'd like to do is, using some of the skills and concepts that we already have, we'd like to have a clear-cut and precise way of saying, okay, this is what it means to be continuous, right? This is what it means mathematically to be able to draw a function without taking your pencil off the paper. So to do that, it's sometimes helpful to look at some situations where things are clearly not continuous, and by looking at enough of the non-examples, you can sort of create some rules that have to be the case in order for a function to be continuous at a certain point. So what we'll do is take a look at some of these situations and see if we can determine the points where it's not continuous and thereby develop our definition of continuity. Okay, so spend a couple of minutes taking a look at this function, and your goal is to locate all the points where the function is not continuous. Okay, so remember, our definition so far is just any part of the function where you can draw it without lifting your pencil off of the paper. So locate these points of discontinuity and see if you can come up with a mathematical way of saying this is not continuous. Something more rigorous than, well, my pencil had to come off the paper. Okay, so there are a couple of spots where it's pretty clear that the function is not continuous. So for an x value of 1, notice that I would have to lift my pencil off of the paper. So clearly when x is equal to 1, we have a discontinuity. Similarly, when x is equal to 2, we have a discontinuity, right? Again, I'd have to take my pencil off of the paper. So when x is equal to 2, we have discontinuity. And also notice that if we go to the left of 0 or to the right of 4, the function is not defined at all. So it clearly, I mean, I can't even draw it if I wanted to. So this would also seem to be places where f is not continuous. So let's go ahead and let's drill down onto these points where we decided it's discontinuous, the function is discontinuous. And let's think about how we might say why, mathematically, it's not continuous. So, thinking about piecewise functions from the perspective of the limit has been really helpful in the past, right? And so let's kind of continue that. And let's think about, if you had a point where it's discontinuous, well, what is the limit like as you approach that x value? So here we notice that the limit as x approaches 2 does exist, right? That limit is 1. But why is it discontinuous? Well, it's discontinuous because actually at 2, your function is not at 1. The value of the function is at 2. So here we could say that the function is discontinuous because the limit, while it does exist and is 1, is not equal to the value of the function, right? So that's actually pretty much the way that we define continuity. And if we look at the function at 1, at x equals 1, and we decide this was discontinuous as well, and let's think about why that is. Well, let's look at it from the limit perspective again. If you look at the left-hand limit, that is 0. But the right-hand limit, as I approach 1 from the right side, that is 1. And so the limit as x approaches 1, the two-sided limit, doesn't even exist. And so it would seem to make sense, like if the limit doesn't exist, how could the function possibly be continuous? Because that means as I come from the left and as I come from the right, the function is approaching two totally disparate values, two different values. And so there's just no way that a function could be continuous if that's the case. And so this leads us to a formal definition of continuity. Alright, so here we have the definition of continuity at a point. And to help us understand the definition, I've drawn an example. And so here you have some function f, and a function is defined on an interval. And so what that means is that there's a certain set of values for which you define the function, that the function exists. And so that means there are two types of points. You can have an endpoint like A or B, or you can have an interior point like C. And obviously for an interior point means that there's going to be some point to the left and some point to the right. For an endpoint, for example, the left endpoint A, there's no point to the left. And for the right endpoint B, there's going to be no point to the right. So that's what it means to be either an interior or an endpoint. So now we have a definition for continuity for both types of points. The ones that we're probably most commonly going to see are interior points. And so a function f of x is continuous at an interior point C, which is in the domain, must obviously be in the domain, if the limit as x approaches C of f of x is equal to the value of the function f at C. And this should be exactly what we just discussed, right? The limit as x approaches C, meaning that the limit as you approach C from the left and as you approach C from the right are equal. That's what the two-sided limit means. And that the value of the function at the point C is the same as the limit, right? Meaning you have this nice smooth curve here. Embedded in this are a couple of criteria, actually 3 criteria, and this would be a good thing to write down because sometimes it appears in the form of a question. So what has to be true in order for a function to be continuous? Well, first off, the function actually has to be defined at that particular point, right? If it's not defined, if it's undefined when you plug in C, there's no way for it to be continuous. So that's the first criteria, f of C is defined. The second criteria is that this limit actually exists. If it doesn't exist, there's no way for it to equal the value at C. And then the last criteria is, of course, the one we've written, which contains those other two, and that is that the limit as x approaches C of f of x is equal to the function at the value C. Okay, now let's talk about the endpoints. And the endpoints, the reason that we can't use the same definition is that the two-sided limit isn't going to exist here because you can't define the function to the left. Over here, you can't define it to the right. And so we have to amend our definition. So we say that a function f of x is continuous at a left endpoint A or is continuous at a right endpoint B of its domain if, and so for the left endpoint, all we want to know is the limit as we approach from the right, the only side we can actually approach from, of that function f of x equal to the value of the function at that endpoint A. And then for a right endpoint, same idea, just a different side, is the limit as x approaches A now from the left, the only side that we can actually take the limit of that function from, is that limit equal to the value of the function when you plug in that endpoint B. Okay? And so that's the definition of continuity. This is something that is tested all the time in sort of creative ways. You'll have, these weird multiple choice questions, but so long as you know this definition, you'll be able to decipher it and decide what has to be the case, what has to be true. All right, so let's practice with the greatest integer function. So this function may be new to you. It's also sometimes called the floor of x, and pretty simple idea here. So if you input some x value, the y value that you're going to get is going to be the greatest integer that is less than or equal to your x value. So as you can see, for example, if my input value is 1.5, it's going to return 1. My input value is 2, it's going to return 2, so on and so forth. Anyway, so your goal is to identify the points where the function is not continuous, and then write the intervals where the function is continuous. So go ahead and give this a try on your own. Use the definition of continuity at a point to determine whether something is continuous or not. So don't just say, oh, this looks like a place where it's not continuous. Make sure that you have a reason, and then we'll go ahead and we'll talk about it. My guess is you had no trouble identifying the points where the function was discontinuous or not continuous. Clearly at x equals 1, 2, 3, and 4, the function fails to be continuous. The important piece here is that you're able to identify and support your answer with a valid reason. So if a function is not continuous, then one of those criteria of continuity at a point must not be met. So if you go through and you take a look at that criteria, right, what we need is that the limit as x approaches a value is equal to the function value for that x input. And this is not the case, right? So if I look at x equals 1, let's see if we can find the limit first. Well, to find the limit, I have to find the left-hand limit, which is 0. And if I then find the right-hand limit, that is 1. And so the limit doesn't even exist. So there's no way for me to say that the limit value is equal to the function value. So very clearly it's not going to be continuous. So for example, if I were supporting my reasoning for x equals 1 being a point of discontinuity, what I would say is that the limit as x approaches 1 from the left of f of x is unequal to the limit as x approaches 1 from the right of f of x. And so therefore, the limit as x approaches 1 of f of x does not exist. Right? And if the limit doesn't exist, it is impossible for us to say that it is equal to the value of the function at that point. And so we have a point of discontinuity. Now, moving on to where the function is continuous, what we're saying here is that if we're saying the function is continuous on a certain interval, that means it's continuous at every single point in that interval. And so if we were to find the limit at any point on this interval, it would be equal to the value of the function for that particular point. And it's pretty clear that between 0 and 1, any value greater than 0 but less than 1, that's going to be the case. And greater than 1 but less than 2, greater than 2, less than 3, greater than 3, but less than 4. Okay? And this should be fairly straightforward, right? If it's going to be continuous on an interval, it's going to need to be continuous at every single point within that interval. Alright, as you may have noticed, there are different ways that a function can be discontinuous at a point. And what we want to do is classify these different types of discontinuity, because some of them are actually, as we'll see, fixable, while some are a little more severe and will not be fixable. So first type of discontinuity is called a removable discontinuity. And here's an example of a removable discontinuity. So the function here is not continuous at x equals 1, right? It's undefined for x equals 1. But the limit as x approaches 1 from the left and as x approaches 1 from the right are equal to each other. So the limit as x approaches a will exist, but it will not be equal to the function value at that point. So notice here the limit exists, the limit is 1, but the function value at 1 does not exist, it's undefined. So there's no way for this to be continuous at that point. Another example of this might be if the function happened to be defined, say, at a different value. So here the limit again still exists and is equal to 1, but f of a, f of 1 in this case, would be equal to 0. And so the limit would not equal, the limit value would not equal the function value, meaning it would be discontinuous. However, these types of discontinuities are removable, meaning you can make this function continuous with one small change, meaning you can remove the discontinuity. And the way that you can do that is you can define your function f of a to be equal to the limit value at that point, right? So we could say, hey, instead of saying f of a is equal to 0, or sorry, f of 1 is equal to 0, let's instead say that f of 1 is equal to 1. In other words, we'd be filling in our open point, and now all of a sudden the limit as x approaches 1 is 1, and the function at 1, f of 1, is equal to 1. And so this would be continuous. So this next type of discontinuity is called a jump discontinuity, and this is what we saw in that last example, and it looks just as it sounds. A jump discontinuity appears when you see the function sort of take this jump, right? At one place it's defined down here, right? And then all of a sudden, when x is equal to 1, there's this jump, right? And it's defined somewhere else. And so a jump discontinuity is a little more serious, because as we saw in that last example, the reason this is discontinuous, the first reason that we come across, is that the limit doesn't exist. So as we're trying to find the limit, we look for the left hand and the right hand limit, and we see that those are different values. And so the limit as x approaches a from both sides, the two-sided limit, doesn't exist. And so it's impossible for us to have a continuous function. And here we cannot just remove the discontinuity, right? I can't all of a sudden just define the function at a certain point here and make the discontinuity go away, right? In order to change this, you would actually have to change the function. So a jump discontinuity is different from a removable discontinuity, because you can't just all of a sudden make the function continuous at that point. Okay, the next type of discontinuity that we have is what's called an infinite discontinuity. And so taking a look at this example where we have the function 1 over x minus 1 quantity squared, and here there's an issue where we have a vertical asymptote at x equals 1. And so if I'm looking at the limit as x approaches a of our function, you'll notice that either the left or the right side limit, in this case both, are going to equal positive infinity. And so if we have a situation where either of the one-sided limits is equal to plus or minus infinity, then it's going to be impossible for our function value to be equal to our limit value, right? There's no way that we're going to have a function defined for x equals 1 in this case, or x equals a in either of these cases when the one-sided limit is equal to positive or negative infinity. So it's called an infinite discontinuity. The last type of discontinuity we have is what's called an oscillating discontinuity, and again, the word there, oscillating, gives us an idea of what this will look like. The traditional function that is an example for this is the sine of 1 over x, and looking at the continuity at x equals 0. And the reason that, as you can see, and if you want it, you can try plugging in values really close to 0. What is happening here is that both one-sided limits don't in fact exist, because it appears that from each side you're actually approaching different values at the same time. As interesting as that, weird as that sounds, you can kind of see that from the graph, right? It's almost as if you're approaching 1 and -1 at the same time. And obviously that makes it impossible to define the limits. So both one-sided limits do not exist for this function as x approaches 0, and so obviously the function is not continuous at x equals 0. So those are the types of discontinuity. There are 4 of them. It's important for you to understand not only what they look like, but also specifically what each one means about the different criteria for continuity, because some of them will react kind of in different ways than others. And for example, a removable discontinuity you'll be able to fix, whereas some other types of discontinuity you'll sort of be stuck with. So now let's go ahead and try a couple of questions out that you can then debrief tomorrow morning. All right, so go ahead and give these a try. A couple of words, hints here. For number 1, really focus on being specific and answer this question without looking back at your notes. Then perhaps go back and look at them and kind of keep both of your attempts down on your paper so that you can sort of see how you're doing with your ability to remember the different criteria. And then for number 2, use your answer to number 1 to sort of inform your answers for parts A and B, right? Refer to the different criteria for continuity in order to support your answers for number 2. Okay?